Hey everybody. Here we go. We're gonna get right into this video here. In this video, we're gonna be doing this Q3 midterm review. I'm not gonna do all of it at once. I'm gonna break it into two parts. So this is the first part, which will cover the question types that will be seen on the first part of the midterm, because we're breaking that up into 2 days. So we're gonna get through about half of these, a little over half. No, wait, a little under half. All right, here we go. First question. Simple enough. If you've got multiple things multiplying together and they have the same base, in this case y, you add their exponents. So 5 plus 5 plus 1, the y without an exponent still counts as a 1, makes 11. So it's y to the 11. Simple, right? Easy question, easy score. Here's a slightly advanced version of that problem. -7 times 5 is -35. So if there's numbers out front like these, I multiply those together first. And then I do like I did on the previous problem, I multiply these u's together by adding their exponents. So I get u to the 4th. Again, the 3 adds with what is essentially a 1, and together they make 4. Man, that's really easy. 2 easy questions, I hope, for you. Another exponent property we learned about this semester is when you divide, you subtract their exponents. So here it's 6 and 2, so 6 minus 2 is 4. Just like that. And then here's an advanced version of the division, which is going to probably require that I make a fraction. So first with the numbers 24 and 8, those divide to make 3. Now I've noticed people also had problems wherein the bottom number was bigger and you have to reduce the fraction. Like if this had been 8 over 24, I would make this 1/3. But in this situation, 24 divided by 8 is 3, so I will put a 3 on the top. If you're not sure where to put something when it comes to reducing a fraction, put it on the top. Unless your bottom number is bigger, then you probably should have more on the bottom. Okay, that being said, the next thing is y over y to the 4th. You subtract the exponents, but in my case, I get y to the -3. Now, you're not actually allowed to have a negative exponent, because I did 1 minus 4, I get -3. So the correct thing to do is, instead of writing it as a negative exponent on the top, which is the default place to put it, you write it as the positive version of that, y to the regular 3, on the bottom. Same thing's happening with z. I got 2 over 5, so 2 minus 5 is -3. So I get z to the regular 3 on the bottom. Think of it this way. There was 3 more on the bottom than the top. Does that make sense? I gotta be honest, I helped some people today, and they had a lot of ones where the letters ended up on top, which seems like the more likely thing. I guess I got an unlikely case, but I'm glad I got to show it to you. Next, we have the power of powers rule. So when you have exponent raised to more exponents, you multiply them together. So v to the 25th. Do not do 5 to the 5th power, which is, what, 3,625 or something like that? I don't even know, man. I'm just saying, don't do 5 to the 5 times 5 times 5 times 5. No, just do 5 times 5 once. 5 times 5, 25. Done. Hey, exponent property is pretty easy, you know? All right, now we're going to do a slightly advanced one where there's multiple things in there. Here, you get 8 squared and y squared. They both receive this squared. So here you get 8 times 8. You know what? I'll use my tablet on this one. I haven't used it on any problems. Here it seems appropriate to do. So 8 becomes squared. Y becomes squared. 8 squared needs to be changed to what it literally equals. And y squared is y squared. So I get 64y squared. So far we've just done exponent properties. Okay, now for some square root properties. Here it seems like writing more would be useful, so I will. So I got the square root of 75, w to the 14. So for these ones, you want to simplify what's in the roots. You can't take the square root of 75, but you can break it down. So 75 is 25 times 3. 25 is 5 times 5. If there's a pair of something, that's good. That'll be part of my answer. So my answer will have a 5 on the outside, and any unused stuff, like this 3 here, will be left behind in the root on the inside. Now that just deals with the number. So 75 in the root turns into 5 root 3. But what about w to the 14? Well, when it comes to variables, you can write W 14 times and circle each pair, or just do this. How many times does 2 go into 14? The answer to that is 7. So W to the 7 can come out. Now notice this was an even number, and 2 goes into it evenly, and therefore I wrote some results all on the outside. If it had been an odd number, there could be a remainder left on the inside. That didn't happen on this problem, but I'm pretty sure it will happen on the next problem we see, so it is what it is, and we'll see it when we see it. So I did a factor tree to take some stuff out. I was left with some on the outside and some on the inside, and then the W's, I divided it by 2. You want to divide it by 2. That's kind of what square root means, because it means a number times itself. W7 times W7 makes W14, but the square root of W14 therefore becomes W to the 7. All right, here comes another one. So let me write that guy down. We got 12y to the 5th, z to the 10th. So in this one, the 12 is 4 times 3, and 4 is 2 times 2. So I get 2 on the outside, 3 on the inside. Please don't reverse these. If it's a pair, it's on the out. If it's unpaired, that means it has to stay rooted. Okay, now for the letters. Y to the 5th. So I want to visualize this one by showing you the y's. If I draw 5 of them, you'll notice there's 2 pairs. So I can put y to the 2 out here. And then there's one unused one that goes on the inside. If we're doing what I was doing on the last problem and thinking to myself, how many times does 2 go into 5? Well, it goes in twice, right? With a remainder of 1. Hence, y to the 2 on the outside, regular y on the inside. Z to the 10, I'll do it the quick way only. 5 is the result when you do 10 divided by 2. So you get z to the 5 all on the outside. No remainders on that one. And there's our answer there. Somehow to me that doesn't look more simplified, but hey, them's the rules, man. So 2y to the 2, z to the 5th, and 3y. In math, the less you have in the root, the more simplified it is, so to speak. All right, so everything we just saw was exponent properties and root properties, like when do you add the exponents, when do you subtract the exponents, how do you reduce a fraction with the exponent stuff in it, how do you do powers of powers, and then how do you simplify root things. Now we're getting on with these problems that have exponent stuff going on, but it's not just simplifying the properties, it's more like finding out exponent, how to graph it, filling out a table, how to make an exponential function. So this first one says g of x, whoopsies, g of x equals 1/4 to the x. Now I'm typing it into Desmos, you'll see. Our goal is to fill out this table. To fill out this table, you simply need to plug in -2, -1, 0, 1, and 2 for x and see what you get. I'm typing into Desmos because Desmos can do that for us, and it's okay to do it. You hit this in here, and you get a graph. The graph doesn't really matter right now. You hit the gear, and you can hit this little button that turns it to a table, and voila, you get some numbers. You get 16, 4, 1. Now you get some decimals, and I got to tell you, Alex will give you a little angry message saying you're not allowed to use decimals. So what do you do for problems with decimals? You gotta fix it, right? And I'll show you how. You type g or f or whatever kind of function letter they gave you, g of whatever the number is that's giving you a weird output. So for example, 1 is giving me 0.25, and 0.25 shows up here, and I'm allowed to click this, and it's 1/4. Now maybe you already knew it was 1/4, so if you know it, just put it, duh. But if you don't know it, this would be a good opportunity to change it. Now if I want to know about g of 2, because that one's also a weird one, change it to, oops, not 21, change it to 2, and I get 1/16. Big shocker here, it's just the reciprocal of what you got when you plugged in those negatives up here. That's very likely to happen, so be prepared to see that on yours. So I plugged it into Desmos, the full function, made a table, and then used the table to help me fill out the chart there. All right, now we're talking about domain and range of a graph. Graphing anything is not going to be helpful at all. Here's what you need to know. The domain of an exponential function is always all real numbers for the following reason. Domain is x values. Like, what kind of x values are possible? Well, that all depends. How far left can the graph go? How far right does the graph go? Is there any place where it stops going left or stops going right? Or there's like a moment where there's something horizontally that breaks it up? No, it goes left forever. And despite the fact that it's dropping, it's still slowly going to the right for forever. So the domain is all real numbers, and that's very common in almost every function you ever see. The only exception to that is maybe a square root function. Okay, the range, however, is restricted. You'll notice the graph does drop forever, but it doesn't ever go any higher than this dotted line. So the range can't be all real numbers. There's no graph that's ever going to be up here. So how do you say that in a math sentence? Start with y, because the range is the y values. And in our case, in this case, the entire graph is below the dotted line, which means the y values are always less than something. They're never going to be greater than this dotted line. So what is this dotted line? Well, it's crossing through -2. So that's what I say. The range of the function, the height of the function, is always less than -2. It'll never go any higher than that. Now, you might need to do greater than. That all depends on if your graph is above the dotted line or below the dotted line. There's going to be a second problem to this, so maybe we'll see it. Nope. So see this one, it's below the dotted line. Now this one's rising instead of falling like the last one, but it's still irrelevant. It's all below the dotted line. So I'm going to do another. Let me just write it first. Y is less than. In this case, the dotted line is crossing at -1. Notice that is the important thing of the range. Please do not mind anywhere where the solid line's crossing. If it crosses through -3, who cares? It doesn't do anything. What matters is it never goes any higher than this dotted line, which is at -1. So it's always less than -1. And again, the domain is all real numbers. All right, this says graph the function. Like any reasonable person, if I have a graphing calculator, I will graph it on that first. Ta-da! Now it says to graph the function on Alex, to make Alex happy, you need to plot the points -2, -1, 0, 1, and 2. Draw the asymptote and click the graph button. Now here's the deal. To get those points on Alex, you'll do what I did earlier with the table. Oh, with the table, sorry, wrong inflection. Make this graph into a table, and you'll see the 5 points, and those are exactly what they want. They want -2, -1, 0, 1, and 2. Ta-da! Now, here's my deal. Decimals here are okay. You can't click on the graph and make decimals. You can click on this little box and type in decimals. So I'm going to type in -2, comma, all that stuff. Now, the question is, though, how far will this let you type? I guess it'll let you type a lot of stuff, right? If you have a repeating decimal, you should not type it into this ever. Like if it's 8.333, don't type 8.33333. That's not good enough. None of my decimals were repeating. Now, if you're in the situation where you don't know if it's repeated or not, just do what I did earlier. Type f of -2, see how it gives you the same thing, and make it a fraction. That's safe. So if you're like not sure if the decimal's okay, just make it a fraction. That'll always be right if you make it a fraction. -1, comma, well, I guess while I've already got this open, I might as well type in -1, right? 1/8. I will say, though, that the decimals that I personally had would have been okay. Here, just to show you, to prove my point, I'll put 0.5, even though that's supposed to be 1/2. That will still be acceptable in terms of the graph. And while I've got this open, I'll do the other 2 regular points. Perfect, I got my 5 points. Now, if you try and click the graph button, it says make sure you draw one asymptote. Asymptote means this. Where's your graph leveling out? See how my graph never goes below the axis? Well, you got to draw a horizontal dotted line to show that it will never go below the axis. Then you click. Easy as that. So similar process to the table earlier. You're gonna want a table so you can get the points easily. The decimals are acceptable to enter on this Alex tool. Unless they're repeating, then you might want to convert them to a fraction by like having the function enter and get the value for you. That way you can put it as a fraction. That'll always be nice. All right, the next couple problems give you a base function or a parent function, and they ask you to graph the new version of it. So this is graphing 3 to the x right now. They want 3 to the x minus 1 minus 4. The stuff on the outside here moves it up and down. So in my case, -4 at the end will move it down 4. So what I'm going to do is I'm going to start at the point that I can see on the graph and literally move that point down 4. That does not mean the point goes to -4. It started at 1, so it's going down to -3. That's 4 less. The exponent moves stuff left and right, but you got to be careful. Minus means right, plus means left. So I'm actually going to go right 1. Now here's the deal. I see people doing this all the time. Y equals 3 to the x. They're going on Desmos, trying to use Desmos to help them graph the problem. And I'm not going to sit there and say this is the worst idea. But if you graph it on Desmos, what ends up happening is this. You end up seeing points like this, and then you start going, oh no, I don't know what to do. Oh, this is crossing here. How do I do that? And then they start trying to drag the point on there and this stuff. This is not, all Desmos should be used for here is to kind of make sure your graph shape matches. Like, does my new graph kind of follow? Do these two graphs on here kind of look like these two graphs over here on the Desmos? That's all I can say, right? Like, if I had done something like this, that definitely doesn't look like these graphs. Or if I'd done something like this, that definitely tells me that there's something wrong because these should cross and be something like that. So that's all Desmos can do, is kind of just give you a general shape to make sure you're on the right track. You really need to know personally how the negative and positive numbers affect the movement up and down and left and right when it comes to the real deal movement, okay? So let's do another one. 1/3 to the x is being converted to 1/3 to the x plus 2 minus 1. So the minus 1 at the end, I'll start with that. It moves it down 1. The plus 2 in the exponent moves it 2 to the left. Remember, exponents do opposites. Got to remember that rule. Very important. All right, the next couple problems, where are we at? 15. Okay, we're getting close to the end of this segment here. So number 15 says you need to make a function. Now I'm going to write over here the generic form of the function. 1 plus r to the t. This is the generic form of an exponential function. Oh, it comes in two varieties. It could have a plus or a minus. So the plus version is when you have growth, and the minus is when you have decay. You have to read the problem words to decide which kind of thing's going on there. So on this problem, I'm going to start with y equals. The a value is the start value. So what do you start with? 600 milligrams of radioactive substance. So that's what we'll start with. In the parenthesis, notice the equation by default always includes a 1. That represents you starting at 100%. Like you're keeping 100% of 600. But you're not really keeping 100%. You're either gaining a little to it or losing a little from it. That depends on the words. Mine says the sample has decayed by 5.7%. So that would tell me to use a minus instead of a plus. And I'm going to do 5.7%, but you cannot type 5.7 like this. That's wrong. You got to turn that percent to just a decimal. If you're not sure what to do, you move the decimal 2 spaces to the left, or on a calculator, simply divide it by 100. Like, think about it. If I move the decimal twice left, I'd get 0.057. Got to be able to convert there. You're going to have a hard time. And then you raise that to the t power. We're not filling anything in for y. Y is like a thing you would find. And t is like a number you'd plug in if you wanted to know about a certain amount of time. They didn't want that here. They just wanted us to make a generic equation. You'll notice the inside here could be combined, but I'm not going to because it's actually acceptable to do it this way. Okay? If you want to go on a calculator and do 1 minus 0.057 and put 943 like that, that would be okay too. That wouldn't be wrong. All right, this time they gave me a function they want to know about it. So what's the initial population size? Well, that's the number that goes out front, right? The a value. So here we got 230. Then it says, is this growth or decay? Well, the number on the inside here dictates that. If it's over 1, it's growing. If it's under 1, it's decaying. So I have decay. And by what percent does it decay? Oh, the amount of people answering the decay ones by putting 66% because they see 0.66. That's very wrong. No matter what number you have in here, bigger than 1 or less than 1, what you need to know is how far is it from 1. So my advice to you would be take the number you have in there and subtract 1. If you get a negative like I did, that definitely confirms you have decay because it's like negative or whatever. And then you convert that to a percentage. So this 0.34 is 34%. If you're keeping 66%, you're losing 34% every year. All right, suppose a student loan is loaned at this much compounded monthly. What is the amount owed after 8 years? Now, sounds bad because loans are bad, right? But it's not decay, it's still growth. It's growing how much you have to pay, which is, in a sense, bad, but it's still growth, right? This formula is a little different. I mean, kind of structured the same way. So A equals P, 1 plus R over N to the NT. This is the formula. This is a compound interest formula. P is the starting amount. So I'll fill that in for our problem, 2,000. 1 is in there, kind of like the last problems that we had. And then you put the rate, 9%, 0.09. Now this is where there's a difference. Compounded monthly gives away that it's compound interest, because they use the word compounded. You have to include that in there by using that for the letter N. But you don't just put whatever. Monthly would refer to how many times per year. So monthly is 12. So I'll put that over 12. And then in the exponent, I'm going to raise it to the 12 times 8 because I want to know about 8 years, right? Now, I just want to show you this. This is not going to work out for me, but I'm showing you. If you do 12 times 8 like this on Desmos, because you're using Desmos, supposedly, it doesn't stay in the exponent like it's supposed to. And there's no way to make it not do that unless you put a parenthesis, then do 12 times 8 like this. Or if you have the foresight, you could just figure out what 12 times 8 is. It's 96. And if you want to do that, that's fine. I'll give you the same answer. Oops, 12 times 8. Okay. Notice, though, the number of times it does per year, also shows up in the exponent. That has to happen. You're not going to get it right. So I get 84. It says round to the nearest cent. Keep in mind, the nearest cent does not mean the nearest dollar. It means 2 places after the decimal. So 84. Although you should always check. I have a 2 after the 4, so that rounds it down to 84. It could have possibly been necessary to round it up, but not in this case. All right, that covers the 17 problems I want to do. This next problem begins the polynomial stuff. So everything we saw up to this was exponent properties. So the first bunch of problems we saw, here, I'll click through them so you guys can see them a little bit. We had times where you add the exponents, an advanced version of adding the exponents. We got subtracting the exponents. We've got subtracting the exponents and simplifying stuff a little bit more advanced. We got powers of powers. We've got a little bit advanced powers of powers. We've got your roots correcting. We got slightly different root correcting. We've got filling out a exponential functions table of values. We've got finding the domain and range. We had 2 of those. Oops. 11. Okay, then on number 12, we had graphing an exponential function completely. We had 2 where we had to find the translations or the shifts on the graphs of exponential functions. We had 1 where we had to write a formula for an exponential function. 1 where we had to analyze a formula as growth, decay, what's the initial amount, what's the amount it's changing by. And then we had a compound interest problem here for number 17. Hey, that's a lot of things, but we've had a big semester, and we spent a whole month learning these 17 kinds of questions. Actually, some of them are a little bit repeaty, but whatever. But those are the concepts we learned in the first half of this quarter, I should say. So we will get to another video a little bit later regarding the polynomial stuff. And I get the feeling that one's going to be longer because A, there's more questions about it, and B, honestly, they take more time to answer. So I'll be putting together a good video for that later, I'm sure. All right, for now, I'm going to hit the pause button here, and I'll call this video part 1, and we'll get part 2 up there very shortly. All right, see you on the next one.